But we cannot generally define it to have eigenstates of projection of angular momentum along space-fixed axes. It only has, it's only eigenvalues of projection are defined relative to the direction of propagation. And it has either +1 or -1, but not 0. But it doesn't mean that I can't drive projection 0 along some space-fixed axis, right? I can drive a pi transition, which that just means that the electric field is oscillating along the z-axis linearly, which of course is a superposition of sigma plus and sigma minus relative to the k-axis. Okay, right. So we summarize this in what we call the electric dipole selection rules, or this is sometimes known as E1 for reasons that I'll explain in a moment. Which we summarized as follows. So let's say that I have, let's talk about atoms with good quantum numbers as follows. So if my good quantum numbers are L and M sub L, okay, S M sub S, I M sub I, if everything is uncoupled, then if I have, so I have some excited state like this, then the selection rules are as follows. M sub L prime can equal M sub L or M sub L plus or minus 1. And L prime has to equal L plus 1 or minus 1. We would generally, from addition of angular momentum, say that we could also go for L prime same, and that would satisfy this Clebsch-Gordan coefficient, which would be adding 1 unit, right? And I can do that, but this is forbidden by parity. It's a different symmetry. So I have to change L by 1 unit, either up or down, the total L. If the good quantum numbers are J, L, and MJ, okay, then in that case, J prime can be J plus 1 or minus 1, or it can be the same J. But no J prime equals 0 to J equals 0. I can't start with a state with total 0 and end with total 0. That's impossible, because the photon carries 1 unit of energy. And if my good quantum numbers are J, or F, J, L, and MF, oh, and by the way, of course, MJ prime has to equal MJ plus or minus 1, or the same for pi transitions and sigma plus and minus. And similarly here, F prime can equal F plus or minus 1, or the same F, but no F prime equals 0 to F equals 0. And M sub F, again, changes by plus or minus 1, which stays the same for pi, sigma plus or minus. So these are the dipole selection rules. And if we don't satisfy them, we say it's a forbidden transition. Okay? Well, things in life that are forbidden aren't necessarily completely forbidden. Why? Why not? Well, so now what we want to do is we want to go beyond and say, what if we violate these rules? Okay? So for example, suppose let's consider, you know, we have something like this. Say, let me draw the spectrum of something like an alkali atom. Has some NS, this is the ground state, right? For hydrogen, this is the 1s 1/2. For lithium, this is the 2s 1/2. For sodium, it's the 3s. Potassium, 4s. Rubidium, 5s. Cesium, 6s. Okay? The only thing I know is the alkalis. I can kind of do blue too. Then we have up here the and the P1/2, and there's a fine structure splitting, and 3/2. Right? Of course, these things all have hyperfine splitting on them, depending on the nuclear spin. Then up here, I might have a D state, which is L equals 2, right? And if L equals 2, it's an alkali, has 1 unit of spin angular momentum for the electron. So what are the possible J values? So this is L equals 1, this is L equals 2, right? L equals 2, and then I add a half to it, so I can have 5 halves. I could have, let's just write it here. And the 3 halves. And that's all I can have, right, in this case, right? Because spin is a half. Okay, so those are the possibilities. Okay? So, question. If I drive with a laser between these two, which are allowed transitions?
P3 halves to P1 half, 5 halves.
So this is allowed.
To 5 halves?
Why not? So what are the selection rules?
Yeah.
Delta L can be 1, that's cool. And delta J could be 1, that's cool. What about this to this, is that all right?
Yeah.
Sure, because J can stay the same. What about from here to here?
Yes.
Yeah, that's cool. What about from here to there?
No.
No, ixnay with the laser way. Right? So that's a dipole for electric dipole for band transition. What about this state to this state? No. So these transitions are what we say they're forbidden transitions. They're actually electric dipole forbidden. Yeah.
Could you do that 2-photon process to kind of use that imaginary way of going to the intermediate stage and then all the way to the top?
Yeah, so that's an interesting question. We'll come back to that in a moment. So we have to think about the selection rules for that, but that's certainly a possibility, right? So as you said, if I put on 2 photons that were written here, then there is an allowed electric dipole transition to here. So I can virtually excite to that. And I could, or in principle, and then from the second virtual transition, go up here. So if I had 2 frequencies whose sum adds to that, I can absolutely do that. I do that all the time. But suppose, we'll come back to this, suppose I shine on light at this frequency, resonant at that transition. What will happen? Well, as you said, it's electric dipole forbidden. But that doesn't necessarily mean that it's completely forbidden. Just means the electric dipole moment vanishes, right? Because why does the electric dipole moment vanish? Because of the Wigner-Eckhart theorem. There's no way that you can just, with the dipole operator, which is a rank 1 vector, which has 1 unit of angular momentum, get from something that's 0 equals 0 to this. So we want to think about the beyond the electric dipole approximation. We had the multipole expansion. So what we did at some point, kind of very rapidly without looking at the detail, is said if I took the fundamental interaction of a charge with the field that we wrote in terms of the vector potential, and then we did a expansion of the charge distribution under the assumption that it was well localized relative to the wavelength, we end up with an interaction Hamiltonian that we were able to express as follows. Okay, so we have the electric dipole moment. We have the magnetic dipole. We have the electric quadrupole moment. We would have a magnetic quadrupole moment. The electric octupole moment, etc., etc. And we just took this term in our study of what the absorption was, because this is the dominant effect. This multipole expansion is valid, this term dominates, and so forth, when the wavelength, or whatever the scale over which the field is changing in space. So let's just say if A0 is the size of the charge distribution, then the multipole expansion is basically saying the following: that if the field changes over some time scale t, that the time that it takes light to travel across the sample is absolutely tiny compared to t. That's what the multipole expansion is saying. Saying there's no retardation effects across the size of the sample. Now, if this were, for example, if the time over which it's changing, say it's oscillating as a function of time with frequency omega, right? Then this is 1 over omega, right? We want this to be much, much less than 1 over omega, right? Which is to say that the size of the sample is tiny compared to C over omega. Right? And what's that? That's the wavelength. It's the wavelength over 2 pi, lambda r. So it's another way to say the same thing. If we're talking about a wave that has a wavelength lambda, then the multiple expansion is often written that the wavelength of the light is huge compared to A naught. But that's equivalent to saying that the time it takes light to propagate across the sample is tiny compared to the time scale over which the field is changing. Okay? So, we've made that approximation, and under that approximation, this is the dominant effect. What about these other effects? Well, they're possible. They're just generally smaller. Yeah?
In the general case, it will be A naught over V, where the speed of light is dependent on the medium it's traveling through, right?
This is all very order of magnitude stuff. I'm not saying that this is, when we're talking about much, much less than I'm not talking about, small effects like the index of a fraction. This is really all about the fundamental interaction of the field and matter. Okay? So this is not an equation, it's an inequality here. I'm being loose about factors of 2 pi and so forth.
Is that last line accurate as well?
What's that?
Is that last line accurate as well? It doesn't seem like your words.
I'm not sure. I'm sorry, I didn't understand the
Lambda is
question.
much greater than A naught.
Yeah.
Well, omega lambda, 1 over lambda is much greater than A naught.
Yeah.
Why you flip it?
I'm sorry, this is upside down. That's wrong. 1 over the wavelength, right? Obviously. This is 1 over k. Thank you. All right, so so let's look at interactions that are generated by these other multipole terms. Okay, so let's consider a magnetic dipole transition, which is known in the jargon as M1. So there's E1, E2, E3, depending on what pole. Okay? So this is pole 1, there's pole 2, etc. Okay. So if I have an M1 transition, what I'm interested in is, for example, the transition from some initial to some final. Let me just call it J and J prime. I won't even say whether it's a excited or ground. It doesn't really matter because we know from the selection, what we just did with the dipole, it goes either way. So now I'm going to look at this. So I have some initial state with quantum numbers J and M and some other ones alpha. Alpha could be anything I like. And I have alpha prime and J prime and N prime. All right? And of course, I can write this as I should in the spherical basis, sum over Q the component Q star B. Okay. So I've written this in the spherical basis as we know how to do. All right. So So first of all, this operator is a vector. It is a rank 1 tensor. Right? If these states are eigenstates of angular momentum with respect to an angular momentum operator that generates rotations for which mu is a vector, it's a vector under J, then we can use the Wigner-Eckhart theorem, right? And the Wigner-Eckhart theorem tells us that this is proportional to that, right? Which means that angular momentum conservation, for which the Clebsch-Gordon coefficients are a statement, dictates that J prime can equal J plus or minus 1 or J, and M prime is M plus Q, where Q is either plus 1, 0, or minus 1. Right? Just as before. And no J equals 0 to J prime equals 0. Okay? But that's just what we had for electric dipoles. Well, this part is true. That's the same, I mean, the electric dipole was a vector as well. So the vector gave us exactly the same selection rules relative to angular momentum conservation. However, there was another part of the electric dipole selection rules that came from parity. It's a different symmetry. And that also dictated part of the selection rules. Okay? How does the magnetic dipole operator change under parity?
Doesn't.
It doesn't. It's even operator parity. How do we see that? Well, the magnetic dipole, say for the electron, can have two components. It can come from the orbital, or it can come from the spin. Right? So, firstly, how does the spin operator change under parity? It doesn't. The spin has nothing to do with motion. It acts on a different space. It's the identity on position space. This is really the identity on position and this on the spin space, and this only acts on the position space. So this is that. Okay? What about the orbital angular momentum operator?
It's even.
It's even. How do we see that?
It takes R to minus R and P to minus P.
Exactly. So L is R cross P. Right? So this is equal to minus R cross minus P, which is back to L. So sometimes this vector is known as a pseudo vector because it's really it is parity even, whereas a real vector is parity odd. It's more like a rank 1, the irreducible rank 1 component of a tensor. This is related to the cross product. So because it's, so what we see here is that mu is even under parity, as opposed to the electric dipole operator, which was odd. So what does that mean about any of the selection rules that we had over there?
It changes for L prime.
Right, so it is all to do what happens to L. Right, so if I have a, let's consider a state which has some, where L is a good quantum number. Doesn't even matter whether M sub L is, but let's just talk about. Let's do this. Let's say I have J prime, MJ prime, and L prime. So I've included the fine structure, right? Mu Q. Okay, by the Wigner-Eckhart theorem, no, it's not what I want to do because it will get. I need to look at the part of the matrix on this. It depends on the NLs. So come back. So this is equal to the reduced matrix element times L prime and L prime 1Q L and L. Right? So by angular momentum conservation, this tells me this. Right? But parity tells me I can't change these. L's have to be the same. The L's must be the same by parity. Because if I stick in here a pi dagger pi, right? This guy is even, these guys is -1 to the L plus L prime times the same matrix element. And since this has to equal this, L plus L prime has to be even. So, let's go back over here. All right.
Do you want me to delete this guy?
It's okay. Is this transition allowed by electric dipole?
No.
No, it's not.
Wait,
I mean, by magnetic dipole. It's not. Nope. So this is electric and magnetic dipole. All right. Now, what's an example? Well, if I had another p state up here, there's up here some next n plus 1 p. So this is the next principal quantum number, right? And I could also have the same fine structure. Are these transitions allowed? Well, they're E1 forbidden, but is that M1 allowed?
Yep.
Yeah, because J can change by 1, and L is the same, right? And similarly, I can go here, right? And I can go here, go here. These are M1 allowed. Okay. Other example, let's talk about, let's say now I put in the fine structure. Okay, it's fine, I mean not hyperfine structure, hyperfine. You'd be able to do it. Hyperfine. So this would have some, let's say that the spin was 3/2 of the nucleus. So then I can have an F equals 2 and an F equals 1. Question, is this transition, which would be some, you know, RF or microwave transition, some gigahertz transition, is this an allowed transition? Well, it's electric dipole forbidden, but is it, yep, it's magnetic dipole. So this is a magnetic dipole transition. It's the magnetic field that would drive the states between our magnetic sublevels in the hyperfine mass. Okay. All right. Right. So, summarizing that, M1 transition. I have to have L prime equals L. J prime can equal J plus or minus 1, or J. F prime is equal to F prime plus or minus 1, F, and F prime has to equal NF plus or minus 1, and F, no total F prime equals 0, F equals 0. All right, now let's talk about the electric quadrupole. Oh, before I do that, there is an important question, which is, so I said that, I mean, this was a multipole expansion, which is to say that the lowest non-vanishing multipole dominates. And I said that electric dipole dominates over magnetic dipole. That in some sense, the strength of the transition for an electric dipole transition is much, much stronger. So what does it mean by the strength? So let me ask you the following question. If I put on the same intensity of a laser beam driven on a magnetic dipole transition versus an electric dipole transition, what is the ratio of their absorption rates?
Do we have to do the speed of light, like the way that, you know, magnetic fields sometimes scale that way compared to the...
It does, absolutely. It has to do with the fact that in some sense magnetic transitions or magnetic fields are kind of relativistic effects. I said there that the multipole expansion had something to do with how fast the charge distribution is
So like
changes.
like the overseas?
Exactly, so let's see that explicitly. That's exactly the right intuition. So let's look at consider an electromagnetic wave. Okay? In electromagnetic wave, in the units, in God's units, electric and magnetic fields have the same strength. Okay? So, it's the same strength of the field. They both, you can write E in Gauss if you like. Right? So now I have two transitions. Let's say I have some, you know, excited to ground. I have some dipole transition whose absorption rate depends on this, okay, versus some other transition that's magnetic dipole allowed, whose absorption rate depends on this. Okay? So then the ratio of the absorption rates will just depend on the ratios of the squares of these transition matrix elements. So now I ask you, as a good physicist, to estimate how big are these matrix elements for an atom. So the the matrix elements will be dependent on the characteristic scales. What's the characteristic scale of the electric dipole moment in an atom?
Electric charge times the Bohr radius?
Yeah. Okay. And what's the characteristic scale of a magnetic dipole moment? It's a Bohr magneton, right? The Bohr magneton, we can go back, we did this problem in the first homework. We forgot it already, but yeah, not everybody. Mass of the electron times C. Okay, factors of 2, whatever. And this, so I look at the ratio of these. That, oh, and by the way, what is Bohr magnet? The Bohr radius, it's h bar squared over ne squared, I believe.
Should it be d over e over mu, not mu over d?
Well, it depends what I'm interested in. I'm just saying, let's look at this ratio. This ratio is equal to, so this is h bar squared over ne. So I have e h bar over mc divided by h bar squared over n e over h bars. You recognize that? You better. What's e over hc? The fine structure constant, known as alpha. Right? It's the fine structure constant, which of course is equal to the characteristic speed of the electron over the speed of light. Which is what you expect. If I have, it's always the case, if I have a charge and it has a certain distance, the relative strength of the magnetic dipole to the electric dipole is related to the speed of the charge relative to the speed of light. So it's exactly what you were getting at. So this means that all things roughly equal, the ratio of this to this is down by 2 powers of the fine structure constant, right? So this, you know, it goes like 1 over alpha to the power 2. Okay? So that means, and this is, you know, alpha squared is about 5 times 10 to the minus 5. So a magnetic dipole transition, the absorption rate or emission rate is down by, you know, almost a factor of 1,000,000. So it's a very, it's a forbidden transition. It's not completely forbidden, but it's down by quite an amount. Okay? It also means that the lifetime of the transition, that is to say the spontaneous emission rate, is reduced by the same factor, right? Because it's the same, it's instead of the Einstein A coefficient have the dipole matrix element squared, it will have the magnetic dipole squared, which would mean that it would be a very long-lived state. So if I go back over here, suppose that somehow, some way, I prepared the atom in that state. It could spontaneously emit. There's many ways it can spontaneously emit. It can spontaneously emit back to the absolute ground state. Of course, I'd have to think about the Fs and all of that, but, right? It could also decay like this. It can also decay like that. But the relative branching ratios of those is quite different. Which one do you think is going to be the fastest rate? With what fraction of time will it go back to the ground state versus this state versus this state? Well, both of these guys are electric dipole allowed. So those are both strong transitions. However, this one has a much bigger energy difference. That frequency comes in the cube in the Einstein coefficient. So this is going to be the dominant term. There'll be, next dominant will be this. And then there'll be some tiny fraction of the time that it decays down here because of this kind of. Of course, once it gets over here, what will happen to it? Well, it can't decay this, at least not by magnetic or electric dipole, so it'll decay here and then down to here and cascade down that way. Okay, goody. Now let's talk about electric slide, quadrupole transition. E2. Okay. All right. So now we have the electric quadrupole operator, which everyone knows is, the sum over all the charges. Well, in this case, there's one charge, it's the electron charge. That's the position of the charge relative to the nucleus. What can we say about this? Well, this is a tensor. Moreover, it's a rank 2 irreducible tensor. How do we know that? Well, it's rank 2. It's got 2 indices.
Symmetric and traceless?
It's symmetric and traceless. Okay? Which, of course, I could also transform in the spherical basis into components in the spherical basis. So this is in the Cartesian basis, this is in the spherical basis. We'll come back, talk a little bit more about that in the lecture. So this is, there are 2 times 2 plus 1, or 5 components. Q ranges from -2 to +2. All right? All right, my interaction Hamiltonian over there was sum over I and j, the I component of the gradient of the j component of E. All right? So my interaction depends on this. And I need to then think about So this, of course, we have to look at the specifics of the actual field that's here, but let's say this was a plane wavy thing, right? Then this derivative would be something like 1 over the wavelength, or the wave number, right? So this goes like k times e, something like that. Okay. So my absorption rate, say, depends on the square of this matrix element times something like k squared and e0 squared, right, the intensity. So it goes like that. So firstly, selection rules. By the Wigner-Eckardt theorem, invested in me, I declare that this matrix element is proportional to, not alpha, but proportional to J prime nj prime 2 Q J nj. Right? Which means that what are the selection rules tell me? What are possible values, the difference between j and j prime? Well, j can equal j plus or minus 2. It could equal j plus or minus 1. Or it could equal j. Because I'm adding 2 units of angular momentum, and the final ranges from this minus 2 to this plus 2, absolute value. Okay? Depends, yeah, anyway, let's leave it like that. Right? We'll come back there. Hold on a moment. And of course, what about nj? How can nj's change?
It has to be mj plus q.
Right. And q can be plus 2, plus 1, 0, minus 1, minus 2. So the nj value can change by q. So angular momentum conservation dictates to me that I have these allowed transitions. Now what about parity? Odd or even? Even. So this is even under parity. So what that means in this case is relative to L is what? L can be plus or minus 2. That's okay. This is no variable. And what about this? Well, L can be the same L, but no L to L prime equals 0. So this is fine. That's perfectly fine. So, let's go back over here. S1/2 to D3/2. What do you think about that? That is, it's E1 and N1 forbidden, but it's perfectly good E2 allowed. What about from S1/2 to V 5/2? Sure, because I change L by 2. And if I change L by 2, and I change J, oh, wait a minute. Yeah, J changes by 2. That's cool. All good. All right. Now there's something curious here, though. What about this transition? Well, that's still, that L went to L. Huh, is that E2 allowed? Yes. So there are transitions that for which both. In fact, there will generally be, so let's blow this up a little bit. So let's look at this transition with the sublevels included, the MJ levels. So here I have my n plus 1 P3 halves, which has MJ prime minus 3 halves plus a half. Yeah, that's fine. Minus 3 halves. And my n plus 1, or my n p1 half, what the heck, which has these sublevels. Okay. So, in this kind of transition, all of these transitions are both M1 and E2 because they satisfy all the possible selection rules. In which case, we would have to add the two, take the matrix element, and then square it.
They interfere?
And they will interfere. Okay. However, there is another transition. What about this one?
Only E2.
That's E2 allowed, right? Because with E2 you could change the projection by 2 units. That would be only a quadrupole transition. There would be no magnetic dipole contribution to that. Interesting. Now, how strong are electric quadrupole transitions relative to magnetic dipole or electric dipole transitions?
Alpha to the fourth?
What's that?
Alpha to the fourth?
That's a good guess. You might think so. Let's look at this more closely to see how we would estimate that. Okay. So first of all, what is the characteristic scale of a quadrupole? For an atom? What would you guess? Just looking at the form of it.
A naught squared times B.
Yeah. That's what we got. Right? And so my transition rate, let's look at the transition rate of so my transition rate for an electric quadrupole goes like the characteristic scale of this times k E0 squared, right? Compared to say E1, which goes like the characteristic dipole times E0 squared, right? So what is this? So what we want to compare is compare this times the wavelength compared to the characteristic dipole. That's the ratio we care about, right? So this is E A naught squared times K divided by E A naught. All right? So this ratio is K A naught. But that was the small parameter in my expansion coefficient, in my multipole expansion, right? This is A naught over lambda. So that's fine. But it's only the first power of that, right? In fact, if K is equal to the frequency, or C, what omega do we want to choose? Well, a characteristic omega, h bar omega, here for a characteristic energy scale in an atom, would be the Hartree. Okay? So, we put this back together, we have E squared over h bar A naught times A naught over C. Cancel. E squared over h bar C, which is alpha, the fine structure constant. Did I lose an E somewhere? No. Oh yeah. Where did I lose it? I'm losing it. Yeah, there better be E squared there. Yeah, that's right. Thank you. Yeah, put that on the video. E squared, that's the fine structure. Come on, everyone knows that. All right. Right. So, what we learn here is something that we know from classical electromagnetism. We will know this if we don't know this yet, that electric dipole and then electric quadrupole and magnetic dipole are the same order of the multipole expansion. They come in the same order, so that's why. Now this is true because I assumed something like a plane wave. It's not true in any field configuration. For example, suppose I have a bunch of coils of wire and I make a solenoid. And I then oscillate the field, oscillate the current at some megahertz. Well, of course, I made a radio antenna, and meters away from this thing, it looks like in the far field, the electromagnetic wave that's radiating radios. But inside the coil, it's near field, and the magnetic field strength is going to be much, much, much stronger than the electric field strength. Okay, so if I do that, then inside there, the magnetic dipole driven transition is going to be much stronger than the electric quadrupole transitions. but in the context of something like a wave, where I have a plane wave, like a radio wave or a laser wave, then they're on the same order.
And then the next order will change parity as well?
Yes.
So it's kind of
It oscillates parity and more powers of alpha, each one to the next power of alpha. Okay, question. It was a question that you raised. How in the world are we doing this transition which changes the angular momentum by 2 units when the photon has spin 1?
2 photons?
Yes, a good guess. You might say it's 2 photons, but it ain't. This is 1 photon because it's just 1 matrix. I didn't have 2 matrix elements, right? Where I had the 2 photon transitions. You have the intermediate state.
Does it involve superposition?
Maybe it's everything like the policy position in some way. So physically, where could I possibly get this additional angular momentum from if it's not coming from the spin of the photon? It's not coming from the spin of the photon. Maybe it's coming from some other part of the photon. The orbital angular momentum of the photon. Photons, just like any other particle, can have spin angular momentum. But they can also have orbital angular momentum. So when we write when we say something like the electric field, we can loosely think about this as kind of like the wave function of the photon. Not exactly the same, but something quite similar. And this is related to the spin. And this is related to the orbit. Okay? So we said, of course, that the spin, it only has projections along, because of the transversality, this can only have projection perpendicular to K. Those are the felicity states. This is a plane wave. If we wrote this out relative, this is 1 plus this plus a half, et cetera, et cetera. When we did the electric dipole approximation, we ignored any of the gradient of the electric field over this. And we just took this term, and all of the angular momentum came from the spin. When we're talking about things like electric quadrupole, we're looking at this first term. So this field generally contains spin and orbit. Now, it's not a momentum eigenstate, a plane wave, doesn't clearly have orbital angular momentum. It's actually a superposition of states with definite orbital angular momentum. There is and that's why, Stephen, yes, there is superposition involved. I can write this state as in the following way. This is known as something we won't have a chance to study this year, a partial wave expansion. That is to say that a state with a definite linear momentum is a superposition of states depending on the position direction of the photon in different orbital angular momentum states. And so there is a component that has L equals 2. Or L equals 1, or what have you. And it's, you could say it's the P wave component of the photon combining with the spin 1 to give total angular momentum 2, which allows an electric dipole transition. Of course, this is a small effect because it depends on the variation in the amplitude of this field over the extent of the atom. And that's a small effect. So generally, this is not a big effect unless you make it so. And what do I mean by make it so? Well, so for example, let me come back over here. Suppose I wanted to drive this transition as an electric dipole transition. Well, if I wanted to do that, I would have to have a very good technical capability. Why? Well, the reason is that, let's say that this state is very close in energy to this state. Okay? So this is a very, very, very small energy difference. Then the spontaneous decay rate to this can be very small. Even though it's a dipole allowed transition, it can be a very small rate. Okay? This we already know is very small because it's forbidden. It's only electric dipole allowed. Which would mean that this would have a very, very, very long lifetime. Which would mean that the line width, or the natural broadening of that level, would be tiny. In fact, it's down by 2 orders of the fine structure constant. It might be 1,000,000 times smaller than for this allowed transition. So if this were a megahertz, this would be a hertz line width. It would be a such a narrow line. And poor Jessie in the lab trying to align her laser would need to have a laser that's locked so well that it won't jitter around by more than a hertz. Right? And that's a tough job, but that's what's done. Of course, that's interesting because that would mean that I could do Rabi oscillations, many Rabi oscillations, and coherently create superpositions of ground and excited atoms. As long as the line width is narrow and the lifetime is long. And that's what's done, for example, in Reiner Bloch's experiments in ion traps for doing quantum computing, where the qubit is 0 is the ground state and the excited state is a D state, because it's a very long transition. All right. Welcome to modern history. All right, so that concludes our discussion of, we didn't do everything we wanted to do, but we did a whole lot about absorption, emission, and tensor operators. We're going to conclude the semester by talking about identical particles and many body fields.